Good morning to one and all. In last class, we have discussed about the QPSK waveforms, generation of odd number sequence, even number sequence, and combination of both. We have discussed. In today's class, we'll go for generation and coherent detection of QPSK signal. In that, first we'll consider the transmitter of QPSK, what all it includes. Next part is receiver, that is coherent QPSK receiver, we'll discuss. Coming to transmitter of QPSK, look at this. The QPSK consists of two binary PSK modules. So binary data sequence and polar non-return to zero level encoder is there, demultiplexer is there, and two multiplier, that is two PSK binary PSK transmitters are combined to get a QPSK signal, that is S of t in this circuit diagram. So the QPSK transmitter may be viewed as a two binary PSK generators that work in parallel, each at a bit rate equal to one half of the bit rate of the original binary sequence at the QPSK transmitter input. This is very important point here. Already we have seen in QPSK modulation, the information bits are divided into two sequences, that is odd sequence and even sequences. Expanding on the binary PSK transmitter, as we already discussed, we can build to construct a QPSK transmitter is depicted in this figure. A distinguishing feature of the QPSK transmitter in the block diagram is demultiplexer. The function of the demultiplexer is to divide the binary wave produced by the polar non return to zero level encoder, that is NRZ level encoder, into two separate binary waves, one of which represents the odd numbered die bits in the incoming binary sequence and the other represents the even numbered die bits. Accordingly, we may make make the statement, that is we can use two binary PSK generators to form a QPSK signal here, and phi 1 of t and phi 2 of t are the basis function for this transmitter unit. Next block diagram is a coherent QPSK receiver. The functional composition of the QPSK receiver consist of a pair of correlators. So look at this circuit diagram of QPSK receiver, coherent QPSK receiver. So let we have assumed here x of t is a received signal from the transmitter to channel through the receiver end, that is x of t we have assumed. Then phi 1 of t and phi 2 of t, and integration from 0 to t into dt, and x1 of t will get decision device. Then it is given to the multiplexer, and combination of these two will takes place. Finally we'll get estimate of the transmitted binary sequence. And here we have two channels. One is in phase channels and other one is quadrature channel. So look at this here, demultiplexer is used at the transmitter end, and here we are using multiplexer to combine both. As finally we'll get the received signal, which is same as the transmitted signal. The functional composition of the QPSK receiver consists of these following uh, blocks, that is a pair of correlators, so which have a common input x of t. The two correlators are supplied with a pair of locally generated orthonormal basis functions, that is phi1 of t and phi2 of t, which means that the receiver is synchronized with the transmitter. The correlator outputs produced in response to the received signal x of t are denoted by x1 and x2 respectively. A pair of decision devices which act on the correlator outputs x1 and x2 by comparing each one with a zero threshold. Here it is assumed that the symbols 1 and 0 in the original binary stream at the transmitter input are equally likely distributed. If x1 is greater than 0, a decision is made in favor of symbol 1 for the in phase channel output. On the other hand, if x1 is less than 0, then the decision is made in favor of symbol 0. Similar binary decisions are made for the quadrature channel. So this part already we have studied in binary PSK, where we have used a single decision device and a single correlator. This decision device will come to the conclusion based on the value of x1 to 1 and 0 values of the transmitted bit. Next part or next block is the multiplexer, the function of which is to combine the two binary sequences produced by the pair of decision devices. The resulting binary sequence to produced provides an estimate of an original binary stream at the transmitter input. So this estimate of a transmitted binary sequence is same as the transmitted output at the transmitter end. These both should be similar, so then we can say the probability of error is 0. But based on this decision device, so we may decision device may go to detect ones and 0 wrongly. If the transmitted bit is 1, the decision made device may consider it as a 0. That these type of errors may occur, so that we consider in the error probability of QPSK. So this error probability of binary PSK also we have studied already. There also we have considered based on the decision device output, the error may occur and what is the probability of error. So in this QPSK error probability, so we calculate the following things, and finally we'll calculate the what is the probability of correctness or received uh, reliable received data. Once you know the correctness of the received data, if you calculate 1 minus probability of correctness, will get the probability of error. So that we'll see later. So let consider in a QPSK system operating on an AWGN channel, the received signal x of t is defined as x of t is equal to si of t plus w into t, w of t, where t is greater than equal to 0, less than equal to t for I is equal to 1, 2, 3, and 4, that is quadrature phases, where w of t is a sample function of a white Gaussian noise process of 0 mean and power spectral density of n naught by 2. We see that the two correlator output x1 and x2 are respectively defined as follows. Correlator outputs of x1 is equal to integration of 0 to t into x of t phi 1 of t into dt. If you simplify this equation, so we'll get plus or minus square root of e by 2 plus w1, and x2 is equal to again integration of x of t into phi 2 of t into dt. So simplifying this, minus or plus square root of e by 2 plus w2. So here we are using two basis function, that is phi 1 of t and phi 2 of t, that will be multiplied with this signal integration by taking integration from 0 to t to dt, where t is greater than equal to 0 and less than equal to t, that is considered here. So we'll get the value of x1 and x2 values, that is plus or minus square root of e by 2 into plus w. thus the Thus, the observable elements x1 and x2 are sample values of independent Gaussian random variables with mean values equal to and respectively, and with a common variance equal to n naught by 2, that is probability of density function. The decision rule is now simply to say that S1 of t was transmitted if the received signal point associated with the observation vector x falls inside the region Z1. Say that S2 was transmitted if the received signal point falls inside the region Z2, and so on for the other two regions Z3 and Z4, and erroneous decisions will be made. If, for example, signal S4 of t is transmitted but the noise W of t is such that the received signal point falls outside the region Z4. So these are the problems we can get in this signal. To calculate the average probability of symbol error, we have to uh, consider that QPSK receiver is in fact equivalent to the two binary PSK receivers working in parallel and using two carriers that are in phase quadrature. The in phase channel x1 and the quadrature channel output x2. That means the two elements of an observation vector x may be viewed as in individual outputs of the two binary PSK receivers. Thus, according to binary PSK error probability calculations, the signal energy per bit is equal to E by 2, and the noise spectral density is approximately equal to N naught by 2. We have to consider here. Hence the average probability of bit error of a coherent binary PSK receiver, we may express the average probability of bit error in the in phase and quadrature paths of the coherent QPSK receiver as P dash is equal to Q into square root of E by N naught, where E is written in place of 2 times of EB, considering the binary PSK. So another important point to note is that the bit errors in the in phase and the quadrature paths of the QPSK receiver are statistically independent. Accordingly, the average probability of a correct detection resulting from the combined action of two channels working together, we can write that is P of C is equal to 1 minus P dash whole square, the correctness or correct detection of data, the probability of correct detection of the input signals, that is 1 and 0, that is given as p of c is equal to 1 minus p dash whole square. If you substitute the value of p dash into this equation, so we'll get that is 1 minus 2q square root of e by n naught plus q square into square root of e by n naught. The average probability of symbol error for QPSK is therefore is given by P of E is equal to 1 minus PC. So probability of error, that is P of E, is equal to 1 minus probability of correct detection. If you do, we'll get this. Substituting the value of P of C into this equation, we'll get 2q square root of E by n naught minus q square into square root of E by n naught. In the region where E by n naught is greater than 1, we may ignore the quadratic term on the right hand side, so the average probability of symbol error for the QPSK received is approximated as probability of error for QPSK receiver, that is equal to 2q into bracket of square root of e by n naught. This is the approximated values in QPSK transmission. So basically, considering the binary PSK and QPSK, in binary PSK we have concentrated on reliability of data, that is to reduce the error probability of binary PSK signal. But in case of QPSK modulation techniques, we are concentrating more on utilization of the bandwidth. So in next class, so we'll discuss offset QPSK or power spectra of QPSK signal and offset QPSK signals we'll discuss, and also we simplify this equation into bit error rate of QPSK. What is the bit error rate? That will be discussed in the next class. So thank you one and all.